Welcome everyone. This is another lecture on the stability of equilibrium point, and here we have to emphasize that when we talk about nonlinear systems, we actually talk about the stability of the equilibrium point rather than the stability of the system as a whole, because as we are going to see, at each equilibrium point there could be a different characterization for stability. So in this video I'm going to talk about three main points. The first one is the scope of the systems that we are going to deal with, and basically we are talking about time invariant systems. So I'm going to define the modeling equation of the system and recall the definition of time invariant systems as a start. Then we'll talk about the stability of the origin. Why the origin specifically, and whether this is a special case or could be valid to any other equilibrium point. We will show that by shifting the axes, we can always have new axes where the origin of the new axis would be the equilibrium point for the system, and consequently studying the origin as an equilibrium point is not really anything special, but could be applied to any equilibrium point as well. Now we'll move from that to the definition or the different actually definitions of stability that we may encounter in nonlinear systems, and they are all based on the stability of the origin as an equilibrium points. So we'll see the different types of stability, and we'll relate that of course to what we know from linear systems. So as a starting point, let us recall that we are considering in this course systems in the form f of t, x, and u, and x is a state variable vector which could belong to a space of dimension n, and consequently f, which is called the vector field, also belongs to space of dimension n. T belongs to R, this is time, real time, and U is the set of control inputs or external inputs applied to the system, and that could be in space of dimension m in general. Now it is possible that we express U as a function gamma of time and the state variable x. In that case, we allow for feedback, and that would be in the form of x, and we allow for reference signals to be included as function of time. So if we do that, then we can write the new modeling equation as x dot equals f of t and x, because if I substitute for u in the original equation, the resulting function will be just a function of time and the state variables. Let me call, let's say, f1, and we labeled this system as an unforced system. And also we call that system non-autonomous system. And this is equivalent to a time varying system. But if the state equations is in the form f of x only, and that still allows for feedback in the system in the form u equals gamma of x, then we call the resulting system autonomous system, and that's also called time invariant system. So actually in this video we are going to concentrate on this kind of systems, the time invariant system or the autonomous system. But as a start, let me recall the basic difference between autonomous or time invariant systems and time varying systems. So if I assume that I have here a time invariant system, then it means actually the output of the system will not be dependent on the time at which the input is applied. Let us take a very simple example. If we have like a step input here, say U1 applied to the time invariant system, and we notice the output, something like this, for example. So this is the output due to the first input. Now if I apply a second input but at a different time, like T1, and this is U2, then we will notice that the resulting output will be similar to the first output, except it is shifted by the same amount T1. So we'll get something like this, starting at T1. So if this is satisfied, we call that system time invariant system. And that commonly happens when the parameters of the system do not change as a function of time. Like a counter example to that, when we have, say, a satellite or a rocket, and there is a huge amount of fuel burned during the flight. So we notice in that example that the mass of the object will change with time, and in that case the system dynamical equation will be changing during time, and we call that system time varying system. So a time invariant system is basically a system where the parameters and the dynamical equation of the system do not change of time. However, of course, the state variables of the system will respond to the different external and internal inputs that are applied to the system. So if I like to have here a simple plot for time varying systems, so again, if I have an input here, say U1, and I get the output Y1, if I shift the input by an amount, say T1, what I will get here would be something different, like this, some oscillations or whatever, in contrast to what I have, which is a smooth curve. So this would be a typical example that illustrates the difference between time varying and time invariant system. Now, as I mentioned, we are focusing here on the case of autonomous systems, which are time invariant systems. So this is our scope that we are going to do during this video. When we define the different types of stability or equilibrium points, we are going always to refer to the origin as an equilibrium point. So my objective here in this part of the video is to show that this is not restrictive actually, because we can always shift the axis of the original system to where the equilibrium point lies, and consequently the origin of the new axis will be the equilibrium point. I'm going to show that by a simple example. So let us consider second order system, x1 dot equals x2 and x2 dot equals minus sine x1 minus b x2. These two equations actually mimic the modeling equations of the pendulum. So if I would like to find the equilibrium points of the system, we know that they will correspond to x2 equal to 0 and x1 would be n pi, where n would take the value 0 plus or minus 1 and so on. So if I do that on the original axis x1 and x2, then we will notice that we will have equilibrium point at 0 at pi minus pi 2 pi and so on. So suppose that I'd like to study the equilibrium point at pi and 0. So what I'm suggesting now is to shift the axis so that this would be x2 and this would be the new axis. I'm going to call it y. So I'm going to rewrite the equations now in terms of x2 and y. So I'm going to define y as x1 minus pi. So in this way, if x1 is equal to pi, then y would be equal to 0, which means I shifted the equilibrium point to the origin of the new axis, and in that case my x vector, my state variable vector, will be composed of y and x2. Consequently, we can rewrite the differential equations of the system. So for example, I have x1 dot equals x2, but from the definition here we can conclude that y dot is equal to x1 dot. So I'll end up with an equation y dot equals x2. So this will be my first state variable equation. The second equation is x2 dot equals minus sine x1 minus p x2. So again, I'm going to substitute, this will be x2 dot for x1, so it will be sine y plus pi minus b x2. So that means that this would be my second state variable equation. Consequently, I will have a new set of equations, and the origin is the equilibrium point for the new set of equations. So that's how we typically proceed if we would like to study the stability of an equilibrium point which is not originally at the origin. We can just make the axis shift, and consequently in all of the definitions that I'm going to discuss in this video, I'm going to talk about the stability of the origin, and this is by no means any special case. This is very general because of the shifting of the axis. So let us start talking about some of the basic concepts in defining the stability of equilibrium points. We say that an equilibrium point is stable if all solutions that start nearby the point will stand nearby. Otherwise, the equilibrium point is labeled as unstable. Further, if the equilibrium point is stable and the solution converge to the equilibrium point as t tends to infinity, we say that this equilibrium point is asymptotically stable. In order to illustrate this, let me consider linear systems. And I'm going to consider the second order linear system so we can visualize the solution. So let the system be given by the state space equations x dot equals ax, where a is non-singular and with some initial condition x naught. Now we know that the only equilibrium point that we have for this system would be at the origin. So the equilibrium would be just the point 0 and 0 for a second order system. And the characteristic of the system will, or the operating point in this case, will be dependent on the eigenvalues of the matrix A. So if we have the eigenvalues of A, which are lambda 1, say negative, and lambda 2, negative, we get what we called before stable node. And we know that in this case the solution will decay from the initial condition exponentially towards the origin, which means that if we start nearby the equilibrium point as mentioned in the basic concept, then the system will remain nearby and eventually will go to the origin. So this is asymptotically stable. Also, if we consider the case of lambda 1 say less than 0 while lambda 2 greater than 0, then we know that we get saddle equilibrium point. And in saddle equilibrium point, that we know that there is a trajectory which is along the eigen vector corresponding to the stable eigenvalue. If we start along that eigenvector, we can get to the equilibrium point. But if we start anywhere else, the solution will diverge and will go to infinity. So that is, according to our definition, means that we can classify the saddle point, the equilibrium point, which is the saddle, as unstable. If we consider the eigenvalues of A, where we have minus alpha plus or minus j beta, where alpha is a positive number in this case, that means we are in the stable region, and what we get is a stable focus, and we again will get an asymptotically stable system. So here this is stable focus, and consequently the system is, or the equilibrium point is asymptotically stable. Actually, in linear systems, as I mentioned before, we don't distinguish between the stability of the system and the stability of the equilibrium point, since the system has only one equilibrium point. So if it is stable with respect to that equilibrium point, it is stable as a whole. However, the situation will differ surely when we consider nonlinear systems, and so on. So we can classify the different equilibrium points for a linear system. We have here talked about stable node and saddle and stable focus. We can also talk about unstable nodes where we have lambda 1 and lambda 2 both positive. In that case, the solution will diverge away from the equilibrium point, so it is unstable. Also, we can talk about the unstable focus, where the real part of the eigenvalue will be positive. In that case, also the solution will diverge away from the equilibrium point, and consequently the system is considered to be unstable. For the center, if we have for linear systems, if we have the eigenvalues of the matrix A at plus or minus j beta, in that case we get a center. The center could be classified, since this will be the trajectory, this is x1 and x2, this is the trajectory. This could be classified as a stable response rather than asymptotically stable, because obviously the trajectory will never go to the origin. However, if it starts close to the origin, it will remain close to the origin. Now let us get back to nonlinear systems and try to classify the stability of the equilibrium points. I'm trying here to summarize what we are going to see. So we start by defining the meaning of stable equilibrium point. And as I mentioned at the introduction, we mean by stability that if we stay close from the or the nearby of the equilibrium point, the trajectory of the solution will remain nearby the equilibrium point, but we'll see that in a more formal way. We define also what's called asymptotic stability, and by that we mean that as this equilibrium point has to be stable, and as the time tends to infinity, the solution will also converge to 0. So this is asymptotical stability. Exponential stability implies asymptotical stability. However, the way that the solution converges to the equilibrium point will be according to an exponentially decaying function. This could be also the three types of classes I just mentioned could be classified as local stability, because the region from where we can start is not really the whole space, not the whole state space. If it is the whole state space, then we talk about global stability. So we talk about globally asymptotically stable and globally exponentially stable, and these are similar to what we said here, except that the domain from which the initial conditions could be picked is open. It could be anywhere in the state space. Now let's go to the definition. If we consider a function f of x, and that f of x is a vector field, and it is locally Lipschitz over a domain D, which is a subset of the real space of dimension n, and that space D must contain the origin. So like for example, if I consider here the second order space, this is R2, this is say x1 and x2, then we are saying that D could be a domain within R2, however it has to contain the origin within it. We also require that f of 0 will be equal to 0, which will lead actually to the conclusion that the origin is the equilibrium point for the system x dot equals f of x. Now, if the origin is the equilibrium point, then we say that this equilibrium point is stable if we can select some positive number epsilon, a sphere in the hyperspace of dimension n of radius epsilon. So for this region, we can find a corresponding ball within that, contained in that region, of radius delta, and that delta could be a function dependent on our choice of epsilon. So for that case, the system, if it starts, the initial condition starts within the ball of radius delta, its trajectory in the future time will remain inside the ball of radius epsilon. Let us draw a figure to illustrate that again in the two-dimensional space. This is x1, this is x2. So I'm defining here an open ball of radius epsilon, and within that ball there is another ball with radius delta, such that if we start from any initial condition within the ball of radius delta, the trajectory of the solution will never leave the ball of radius epsilon. So it can move like this, for example, but it will never leave the bigger ball of radius epsilon. So if that's satisfied, then we say that the system is stable. However, if this cannot be found, like for some small ball of radius epsilon, we cannot find the corresponding ball of radius delta such that the solution started within delta will be confined within the ball of radius epsilon. In that case, we say that the system is unstable. Now let us look at an example to illustrate the concept. If we consider the second order system that corresponds to the equations of the pendulum, and we ignore friction, we know in that case if x1 is the angle of rotation, L is the length of the rod, and x2 would be the velocity of the tip point of the pendulum. We know that if we give the pendulum initial velocity and the initial displacement from the 0 position, which is vertically down, then it will keep oscillating around the 0 position, the angle 0, x1 equal to 0. And that will result in a continuum of closed orbits like we have shown here. These closed orbits in green represent the oscillation around the 0 position. However, if the initial condition gets a little bit big, then the solution could move from one equilibrium point to another, and this will correspond to the upper green curves that go to the other equilibrium points. So let's keep it within the equilibrium point at the origin, and we can select now a ball like this one with radius epsilon. Now our objective is to find the region where the initial condition could lie and the solution will never cross the boundary epsilon. What we do is that we look at the closed trajectories within the ball of radius epsilon and see the trajectory, the largest trajectory that does not leave that ball. So in this case, it would be this trajectory up here. This is the trajectory that is confined within the ball of radius epsilon. The one which is above it, it leaves down here, so that's why we can't take it. So we take the biggest trajectory that will be confined within the ball of radius epsilon, and then we determine the radius delta such that it would be corresponding to the minor axis of the largest trajectory within the ball of radius epsilon. In that case, it would be the curve that I'm pointing to here. So the red circle here would correspond to the region where, if I start with an initial condition in that region, the trajectory will never leave the ball of radius epsilon, and that's how we can prove, of course, that the origin in this example is stable. Let me now apply the stability definition to the other equilibrium point at pi and 0. So if we take an arbitrary ball of radius epsilon, this is a ball of radius epsilon, and try to see whether we can find another ball with radius delta from which we can keep the trajectory inside the bigger ball of radius epsilon. So we know actually in this kind of system, since this is a saddle point, that there will be an axis along which the trajectory will go to the origin. However, there is another axis which corresponds to the unstable eigenvalue along which the trajectory will go to infinity. That means that if we take a small pole of radius delta, whatever small that pole, so this is a pole of radius delta, we can always find points within that small pole such that the trajectory will go to infinity, which means that it will go through the ball of radius delta and then through outside the ball that has radius epsilon, and consequently, according to the definition, that point will be unstable, which is of course expected because it is a saddle equilibrium point. So I will stop here, and in the coming video we'll continue the classification of the stable equilibrium points.